Bismillahirrahmanirrahim. I'm very glad today to be with you in this first conference, international conference of sustainable energy and advanced materials, with my modest work titled Impact of the Choice of the Distribution Function of the Prisek Hysteresis Model for Ferromagnetic Materials. And I take this opportunity to pay tribute to my friend and colleague, late Professor Mojawi Murad, and I want to say that without him this work could not have seen the light of day. We began this work then at first by an introduction and the Prisek model, and the next step is the study of the Prisek hysteresis model with analytical distribution function. After that, we present the simulation of hysteresis loop, and after that we discuss the results and at last the conclusion. One day, progresses in simulation techniques has made it possible to better study and understanding the phenomenon of hysteresis linked to the behavior of ferromagnetic materials, which are the major importance for the modeling of and promotion of electrical machines. The well-known Prisek model, and frequently used by experts in the field, requires a numerical or analytical distribution function characteristic of this chosen material. However, the precision of the hysteresis loop is directly affected by the choice of the analytical function and method for determining their parameters. In this work, we have opted for a technique of modeling and simulating the hysteresis cycle of Prisek model by highlighting the importance of the choice of magnetic distribution function. The use of this model is based on choosing the distribution function to calculate the final magnetization of any ferromagnetic material. In this paper, we present a comparative study between the unit distribution function and the Lorentzian distribution function, to highlighting the importance distribution function for the complete and accurate prediction cycle. The Prisek model is one of the most used models to represent the hysteretic phenomenon of magnetic materials, and any other hysteretic system is based on the work of Frank Prisek, which was published in 1935. It appeared to be particularly successful and is nowadays recognized as the best phenomenological approach in describing a large variety of hysteresis in diverse subject areas. The approach of this model is completely intuitive. It's based on the mechanism of magnetization. The basic idea behind it is that any hysteretic system can be put in the form of a combination of several elements called histone, as shown in figure below. At any occupied state of the magnetic field designed by H, the output magnetization designed by M has to be either up or down state. The total magnetization of material is written in a simplified manner as the sum over all histones, as shown in this figure, whose states are defined by the applied field H of T. The total magnetization of magnetic materials is a linear combination of hysteresis operators written in the form of the mathematical expression shown in this page. Here, P alpha beta is the probability density function of the hysteron, which should be determined by the use of some experimental data or by using an analytical distribution. The Price distribution function depends on the nature of the material. It's set to 0 at all points and as limited in its range of definition presented by this triangle called Rechach plane. Now we are going to study the Rechach hysteresis model with analytical distribution function. And you know that several analytical expressions have been proposed for Rechach distribution function, like Gauss, Cauchy, Lorentz. The results of modeling and simulation of a model distribution function using a Lorentzian function compared to unit function are shown in these steps. We begin with unit function. In this case, we use the following distribution function with a variation of external field from the first external field to the second external field, and we have this mathematic expression for the area designed by delta in this figure. Second step, Lorentz distribution function defined by the mathematics expression here with different parameters and shown in this figure. You can see here in this figure that clearly that the Lorentz function is completely defined in the Rechach triangle with the contour plot of distribution function. The Lorentz function in the Rechach model gives this expression. For the simulation of the hysteresis loop in both cases, Lorentz and unit distribution, we have developed a MATLAB code that allows better exploitation of the results and present the hysteresis loop in terms of the induction field versus external applied field using the known expression shown here. Now we arrive to the most interesting part of this paper, the simulation of hysteresis loop, and we begin by the first monetization curve. The first monetization curve is determined from the initial state of the ferromagnetic material. In this state, the domain, the positive domain, S plus, occupies the half of Rechach triangle, and the other half is occupied by the negative domain. The figures shown here respectively present the initial monetization curve generated by the use of the unit and Lorentz distribution function for a variation of magnetic field from 0 to saturation magnetic field, H saturation. And you can see in these two figures the different curves of the first monetization curve simulated by the unit distribution function and the first monetization curve simulated by Lorentz distribution function, and you can see the difference between them. We pass now to the descending branch of the major hysteresis loop, and this descending branch of the cycle of hysteresis is determined from the positive saturation. Its situation is shown in the figure in the next page. The variation of the external field in the direction of decreasing from the saturation field, magnetic field, to value of H1, tripped all elementary hysteron within the range of +1 to -1. This descending curve is obtained by a reduction of the applied field from the saturation level to the minus saturation level, and it is illustrated by the figures in the next page. presenting the distribution, the unit distribution function and the Lorentz distribution function. The first triangle shows the positive saturation state of ferromagnetic materials, and you can see the second triangle when the magnetic field is decreasing in the materials shown in the triangle of Price. The two figures below shows clearly the difference between the descendant branch for Lorentz function simulation and descendant branch for unit function simulation. And you can see the large difference between them. And finally, the ascendant branch of the major hysteresis loop shows the entire cycle of hysteresis, and you can see clearly that the difference between the entire cycle of hysteresis generated by the unit function simulation and the hysteresis cycle generated by Lorentz function. We have described the Plissken model by using the unit distribution function and Lorentzian one. The results shows a significant difference between the two functions. Function unit does not describe the physical phenomenon, while the role of the Lorentz property restores the behavior of ferromagnetic materials. At last, we conclude that in this work we have presented the Plissken model associated with the unit distribution function and associated with Lorentz distribution function for simulate the magnetic hysteresis loop. The magnetic accuracy requires the definition of some parameters related to the magnetic materials and the study obtained all compared to measured cycles. Consequently, the function distribution used in Plissken model should be adequately chosen. Thank you for your attention.